Okay, let's dive into this explainer. Imagine this. It's 2006, you live in an apartment building, and the elevator just crashed. Again. Why? A memory bug in the software. That exact frustration led a developer named Graydon Hoare to start a personal project that Mozilla eventually backed. Today we're talking about that very project, the Rust programming language. It is way more than just a tech buzzword. It's literally a fundamental shift in how we build fast, rock-solid enterprise software.
Here is our roadmap for today. We're going to cover the ultimate programming trade-off, introduce Rust itself, unpack how its unique ownership model changes the game, look at Cargo and the compiler, and finally wrap up with the very real business case for adopting it.
Let's kick things off with Section 1, the ultimate programming trade-off.
For decades, the software world has basically been forced to swallow a really painful compromise. If you've ever managed a tech team or written code yourself, you know exactly what I'm talking about. On one hand, you want raw speed and bare metal control, so you pick a language like C or C++. But then you're constantly fighting costly memory bugs, things like dangling pointers or buffer overflows. On the other hand, you want safety and predictability, so you go with Java or Python. Those use a garbage collector to clean up memory automatically. Sounds great, right? Well, the catch is you sacrifice raw performance, and that garbage collector can just randomly pause your program to do its job. You basically had to pick a lane.
But what if we didn't have to choose? What if you could actually have the blinding speed of C++ and the total safety of Java all rolled into one?
Which brings us to part 2. Enter Rust, where speed meets safety.
Rust proves that high-level developer ergonomics and low-level control absolutely do not have to be enemies. Graydon Hoare actually described his creation as technology from the past come to save the future from itself. And that's because he looked back at decades-old research from the 70s and 80s, languages like Nil, Hermes, and Erlang, to build something incredibly modern. It's basically decades of deep computer science theory finally brought to life with a very practical syntax.
So, the huge takeaway here is that Rust gives you C-like speed using what they call zero-cost abstractions. That means you get to use high-level, developer-friendly features, but they compile right down to raw machine code that runs just as fast as if you'd painstakingly written it by hand. And the craziest part? It does this without the heavy memory footprint, the unpredictable stutters, or the runtime overhead of a garbage collector. But I know what you're thinking. If there's no garbage collector sweeping up, how in the world does it stay safe?
Well, let's move to Section 3. How ownership changes everything.
This right here is Rust's absolute secret sauce, ownership. It's a strict set of rules that the system enforces completely at compile time. Rust uses something called affine types, which is just a fancy way of saying every value is used at most once in a specific context. Every single piece of data has exactly one designated variable that owns it. And because the system ruthlessly tracks who owns what, it makes things like dangling pointers or data races mathematically impossible.
Think of it like a physical book. Only one person can own that book at a time. Now, sure, the owner can temporarily lend it out to a friend. Rust calls this borrowing, but there's a built-in borrow checker with super strict rules. For example, you can let a dozen people read the book at the same time. But if someone wants to write in the book, like actually mutate the data, absolutely no one else can read or write to it at that same moment. That one little rule completely kills race conditions. And this creates a beautifully predictable life cycle for your data. First, a value is created and an owner takes possession. Next, it might be borrowed safely by another function to do some quick work. Finally, the exact second the original owner goes out of scope, like when a function block ends, that memory is instantly and deterministically dropped. No waiting around for a garbage collector, just clean, immediate cleanup.
All right, Section 4, Cargo and the helpful compiler.
Now, an elegant language concept on its own isn't really enough, right? A language is only as good as the tools developers have to use day in and day out. Usually, compilers just translate code and yell at you with cryptic error messages. But the Rust compiler is different. It actually acts like a gatekeeper. Honestly, instead of seeing it as an annoying hurdle, Rust developers treat it like a relentless QA engineer sitting right on their shoulder. It flat out refuses to compile if it spots a memory leak or a concurrency bug. It catches fatal errors right there on the laptop, way before they ever get near a production server.
And that relentless helpfulness carries over to Cargo, Rust's all-in-one package manager and build system. If you have ever tangled with the absolute nightmare of C++ build tools, Cargo is going to feel like magic. It effortlessly handles downloading dependencies, compiling packages, and guaranteeing reproducible builds. It even integrates tools like Rust format to keep your whole team's code looking consistent. It just wipes out that whole messy ecosystem fragmentation you see in older languages.
Let's wrap it up with Section 5, the business case for Rust.
So the tech is incredibly elegant, for sure. But what does this actually mean for the bottom line? Just look at the sheer momentum of enterprise adoption. Rust 1.0 didn't even launch until 2015, but by 2019, AWS was already open-sourcing virtualization tools written in it. By 2021, Google threw their weight behind Rust for Android, and giants like Microsoft and Huawei formed the Rust Foundation. Then, in 2022, the Linux kernel itself, literally the backbone of the internet, started integrating Rust support. Huge companies like Cloudflare and Dropbox are actively rewriting their core systems in Rust to squeeze out maximum performance. And the developers? They are completely on board. Nearly 15% of respondents in the 2025 Stack Overflow survey are doing extensive development work in Rust. But even more impressive, Rust has been voted the single most admired programming language every single year since 2016. The people who use it absolutely love it, and they strongly want to stick with it.
So the ultimate takeaway is that moving to Rust isn't just some vanity technical upgrade. It delivers a massive, quantifiable ROI. You get zero runtime overhead, meaning you can actually downsize your cloud infrastructure. Studies even show Rust code uses significantly less energy than similar Java code. You're going to see dramatically fewer production crashes because those nasty memory vulnerabilities are squashed before the code even compiles. Plus, your developers stay happy. You end up shipping faster, safer, and far greener software.
Which leaves us with one incredibly vital question. Is your legacy code costing you speed and safety? If your team is constantly putting out fires from mysterious memory bugs, rushing out emergency security patches, or paying premium cloud fees for bloated server resources, it might just be time to rethink the paradigm. Rust proves we just don't have to compromise anymore. If the biggest tech giants in the world are rewriting their critical systems, can you really afford to be left behind? Thanks for hanging out with me for this explainer.